So, waiting for people to appear. We are at 5, then I start. Nine. Okay, there we go. So, welcome everybody to this new lesson of probabilistic robotics, this time from home due to COVID. The plan for today is the following. First, we will see a new way of representing probability distributions and therefore a new way of implementing a Bayesian filter, which will be called the particle filter. And then in the second part of the lesson, with Tiziano, we will see an example of the unscented Kalman filter applied to localization that we introduced last time. So introduce the unscented Kalman filter. All right, so let's start. The topic of today, theory topic, is particle filters. Now, before starting with particle filters, I will have to introduce some basic topics that might respond to the question that some of you, which is asking himself how certain primitives of a programming language are implemented are actually function. So let's start with the simplest of the problems, which is sampling from a distribution. Now, very often in the course we were talking about, let's assume that we have a random variable distributed according to blah blah blah, and then we were hiddenly assuming in several circumstances to be able to draw samples from a distribution. What does it mean, drawing samples from a distribution? It means that basically, given a representation of this distribution, we are able to extract a value of the domain of the distribution, which is our random variable, and the probability for this value to occur will be proportional to the value that this that the distribution has in this point. Okay, so in case, for instance, we want to sample from a Gaussian distribution like this one, if we repeatedly ask for samples, we might expect that we will have more values in the middle. So we draw a value, oh, it's here. We draw a value, maybe it comes here. We draw another value, but we might expect that we will have a higher density of samples of these drawn values around the mean of the distribution. Okay, and accordingly, we might also expect that if the variance of this Gaussian is larger, we might have the samples away from the mean to occur more likely than if this Gaussian was having a narrow covariance. Okay, and well, the question is, like, assuming that I am giving you the parameters of this Gaussian, how do you implement a program that is able to generate samples that obey the distribution? That means, in other words, that if you accumulate a lot of these samples and then you want to re-estimate from these samples the parameters of the distribution, then assuming you have infinitely many samples, you will be able to recover the exact same values of mean and covariance that the original distribution had, in case it's a Gaussian, of course, but this conversation holds for any sort of distributions. Now, it turns out that in the basic random number generators are pseudo-random machines that generate sequences of numbers that obey a uniform distribution. So the rand function that you often have implemented in many programming languages implements a drawing mechanism of pseudo-random numbers that obey a uniform distribution, which is a distribution which is constant between 0 and 1. Okay, so each value between 0 and 1 has the same probability of being picked up. Okay, and then assuming we have this machinery, and then the generation, the construction of pseudo-random numbers is a whole other story, but let's assume that we have a basic primitive random number generator that is able to give us uniformly sampled values. Okay, so we have a machine that if we ask him, give me a sample, it will return you a value between 0 and 1, which is with probability likely of any other value between 0 and 1. If you have questions, I assume to have Tiziano in the chat that we will answer, and then I will have a look at the chat at the end of the lesson. Okay, and Tiziano will warn me on the phone in case there is some important topic that needs to be discussed on the moment. Now, said so, assuming that I want to sample values from this P of X, which was parameters I know somehow, and assuming that I have a machine that is able to generate samples between 0 and 1, how can I generate samples from P of X? I observe that from this. Observe that I do have, I do need a machine that gives me some randomness. Therefore, I need to rely on another random number generator, which is the uniform one. Sorry. Which is the uniform one. So, how would you do? Well, let's start from some assumption. We assume to have this density in closed form, right? So this P of X in closed form. If we have P of X in closed form, we can compute the cumulative distribution. And P of X is small P of X is a density, right? And we can compute the cumulative distribution, which is this capital P of X that expresses the probability that a value is below a certain value X. So, assuming that we have a Gaussian distribution like this one, then the cumulative distribution will look something like that. Because each time I have to put in the probability mass of being below this value. So like if the probability density of this point here, the cumulative probability of this point will be equal to all the probability of this point here will be equal to all the probability mass on the left. Okay, so we expect this P of X, this capital P of X, to be monothonically increasing. Now, a very naive way of doing so is to be monothonically increasing and to have its maximum at the value number 1, because there will be a certain number after which that is so high then that the probability of sampling a value below that particular number is basically 1. So this density will saturate to 1. Okay? So now, what we could do, simple mechanism would be to draw a number between 0 and 1. And this we can do it simply by using the random number generator between 0 and 1. Let's call this value y. Okay, so we get a number between this value and this value over here. Let's say we get this sample over here, right? Then what we can do is to project this number onto the cumulative density and pick up the value of the cumulative density that that corresponds to the sampled value y, which means basically that we invert the cumulative density. It's invertible, or it's always almost invertible, because it might have flat regions, because it's monothonic. So we will not have situations like this. And well, and this value x is nothing else than the value of the sample drawn from this probability density over here. Now, to understand the mechanism, or to get a feeling on how it works, you can imagine that the higher the probability density is at a point, the more likely, the more steep will be the cumulative distribution. To the limit, if the density is composed by two Dirac functions, remember that the density must not be invertible, the cumulative must be invertible, then what we would have is a cumulative distribution which is consisting of two steps. Now let's imagine that the density has a Dirac here and a Dirac here. The two Dirac have each a value of maybe 1/2, right? So if I go to and compute the density distribution, I will have 0. Then when I encounter the first Dirac, all my probability, cumulative probability, will jump up to 1/2. And it will stay at 1/2 until I encounter the second Dirac in the density, which let's say it's here. So I will have 0, 1/2, and then when in correspondence of the second Dirac, I would have another 1/2, which bring me to 1, right? So like by doing so, basically I divided the codomain of the probability of the cumulative density in two. There is a region which goes between 0 and 1/2, and another region which goes between 1/2 and 1, right? So like I have a step here, flat until here, and then another step here. Now you might observe that these two regions, they both have they are both wide 1/2, which means basically that if I draw a number between 0 and 1, I will have 1/2 probability of falling in here and 1/2 probability of falling in here. But then, with the mechanism of computing the inversion, I will sample for 1/2 of the time the first value, and for 1/2 of the time the other value. That corresponds to the two steps. Similarly, if these two Dirac were having different magnitudes, so let's say I would have the first Dirac at 1/3, and the other Dirac, so big 1/3, and the other Dirac big 2/3, then the area would be split, this space here would be split into parts. One part which is big 1/3, and one part which is big 2/3. And accordingly, if I sample a value between 0 and 1, I will have 1/3 of probability of picking up the value for which the Dirac is big 1/3, and I will have 2/3 probability of picking up the value for which the Dirac is 2/3. All right, so like this is to provide you how to say intuitive example of the sample generation and why this mechanism works. So rewinding, if I give you a density expressed as a p of x, you could compute the cumulative distribution that gives you something like that, which is a monothonic function. Now, if you want to draw a value from this distribution, you draw a value from the uniform, and then you compute the inverse of the cumulative to get basically the value for which the cumulative has this as a value evaluates to the sample drawn from the uniform that you have just extracted. Now, you could observe that iterating this process for, let's say I want to iterate this process regularly, gives me samples which are denser, where the pendency, let's say this way, the slope of the cumulative is higher, and equivalently where the value of the density is higher. Of course, it matters also for how long the value of the density is higher, because the longer it is higher, the more region I will have covered along the y-axis. Now, if I sample from uniform distribution, now here I have shown just regular samples because it is intuitive. Normally, if you generate samples from a uniform distribution, they will not be equally spaced. They will come in certain order, but if you draw many of them, you will be guaranteed that if you take a certain region in the domain of these samples, the number of samples, the fraction of samples that fall in this domain will be proportional to the area of the domain. So if I take a region between 0.8 and 1, and then I draw 1,000,000 samples, then it's very likely that 200,000 of these samples will fall in the region between 1 and 0.8. This is what you're guaranteed from a random number generator in the uniform distribution. Now you might observe that if I do this mechanism of drawing, going to the cumulative inverting, drawing, going to the cumulative inverting, and so on, you might observe that I have many more samples where the function is steep, which is actually where around the mean of my hypothetic Gaussian distribution. But I repeat, this mechanism holds for generic distribution, and we're not restricted to Gaussians. I just show it with a Gaussian because it's what you're familiar with so far. Okay, so now we know how to sample from a generate samples from a distribution of which we know the cumulative or the inverse of the cumulative and better. Now, if we are in the discrete case, well, the same holds, and actually like this reflects to the game of the Dirac that I was mentioning. If I have a discrete distribution that I could represent as a set of histogram over here, or actually like if I go in the continuum, each of these bars will be substituted by Dirac having a height which is equal to the height of the bar in the histogram, because integrating this will give you a set of slopey things, right? If this was continuous. But you could imagine it as if it was a bunch of Dirac. Here I have just one single value, because I'm in the discrete. You could apply the very same mechanism to draw an index or a value from a discrete set, where each element of this discrete set has a certain weight, a certain probability attached. Okay? How to do that? Well, we mimic what we have done before. We can construct the cumulative distribution. We draw a value between 0 and 1. And then we take this value and we look for the value of the cumulative distribution, for the bin of the cumulative distribution that corresponds to this particular value over here. So of course, in the discrete case, we will always hit a vertical bar, right? And in this case, we pick up the sample that corresponds to the intercept between y and the cumulative, which is discrete. All right, this is how to generate samples, and you could implement this mechanism very easily, for instance, to simulate, imagine that you have a bag with balls of different likelihood, of different probability, right? And you would like to fetch a ball from this bag, and you would like that the heavier ball, so each ball comes out with a probability which is proportional to the weight. One could do that, for instance. So not all events have the same probability. Then how to implement a program that does that? Exactly by following this mechanism, which I think is very simple, because you just have to compute this cumulative distribution, then you generate a value between 0 and 1, and then you look for the bin where the cumulative distribution falls in. If you want to do it efficiently, I recommend you to do a binaries to compute the cumulative distribution, put it in a vector, sort, and then you can do a binary search, because the vector is ordered, in order to find the value that corresponds to the bin that corresponds to the fetched number. Now, this is a possible way, but very often there is the situation where we want to draw from a weighted distribution, so like from a distribution, from a histogram, a discrete probability distribution, not only one sample, but we might want to draw maybe 100 samples, 200 samples from the very same distribution. What are samples in this case? Well, are the values in here, the domain of the distribution, with probability, of course, proportional to the value of the histogram attached to this element of the domain. Then we could do this mechanism, right? That would work, but it's a little bit annoying. And imagine that we have to draw 1,000,000 samples. Well, we are going to invoke 1,000,000 times the random number generator, which is an external library that requires a little bit of calculation. Well, it might be not the most efficient thing to do. And also because then for each of these values we have to run a binary search. So we have the complexity of the random number generator, which is constant but high, and we have the complexity of a binary search to figure out the value of x that falls here, which is logarithmic in the number of bins, in this case, of elements of the distribution. Now, what can we do to solve this problem, to render the machinery a little bit more efficient? I remind you that we want to draw now 1,000,000 samples, or a high number of samples, from a discrete distribution, where the value of a sample will be just the bin 0, bin 1, bin 2, bin 3, and so on. The bin which corresponds to the sample. Like in this distribution over here, we might expect that this element over here will pop up many more often than this element over here, because it has a higher probability. Now, to do this in an efficient way, there's a schema which is called uniform resampling. It has computational advantages with respect to the other schema, because it requires to invoke the random number generator only once. Remember that the samples that we want to produce have to be have to be random, which means that if we run this machine twice, we might expect to have a different order and number of samples generated. What we might expect is that if we draw a lot of samples and then we try to reconstruct the original distribution, then we are able of doing so. But the randomness needs to be preserved, because the randomness is required for some algorithm that you will learn in the remaining part of this lesson. So, how to respond to the problem of sampling 100, drawing n samples with ni from a discrete distribution with uniform sampling. That invokes only that it's an algorithm which has a time linear in the number of samples that you want to generate. It works as follows. Assuming you want to generate n samples, this is your funky cumulative distribution, all here. You draw a value between 0 and between 0, this is a mistake, this is not 1, 0 will be changed, between 0 and 1 over n. Okay? You draw it, from the uniform distribution. So like, of course, in this case, you will select a uniform distribution that spans between 0 and 1 over n. Okay? So it's a uniform distribution which is smaller and taller. Okay? And so you draw your initial value over here. Okay? Then after 1 over n, n is the number of desired samples. So this guarantees you, this action of sampling once, gives you the randomness of the phenomena, because it's the seed of the entire action. If you would run this process another time, well, then you will have a different value of y0. Then after you have this value y0, you start picking up the samples at regular intervals of 1 over n after y0. So sample y0 over here. And then you pick up the next y value at y0 plus 1 over n. And then you pick up the next value at y0 plus 1 over n. y0 plus 2 over n. The third sample, y0 plus 3 over n. And so on and so forth. So in this way, you basically generate the samples on the y-axis instead of calling the random number generator. You generate the first one randomly and all others systematically starting from the first value. Now, for each of these values, you pick up the element of the cumulative distribution that corresponds to the drawn value. So in this case, y0 falls in the first bin, and so you pick up the first element. Then you go to the second element, and the second element falls in the second bin, and you pick up the element x equals 2. The third element, in this case, falls again in the second bin, because the cumulative is this one, right? And so you pick up another time the value 2. The third time, you take this element, and then you pick up the value which is like this was 2, 3, 4. You pick up the value 4. You have been very lucky because you picked up the value 4, like it was very, no, the cumulative density of 4 was very small. Okay? And so on and so forth. Okay? So like this gives you a more efficient schema of implementing of drawing, let's say, a set of discrete samples from a weighted distribution. Observe that from the implementation point of view, this algorithm can be implemented in linear time, because upon one call of the random number generator, you could continue the search by using a pair of indices. One index that keeps track of the current sample, and the next index that keeps track of the y value. And then, so like you start, you pick up the first, and then you advance, you pick up the second, and then you advance the index on the x-axis until you obtain a value of the cumulative which is higher or equal than y, and then you repeat it systematically, right? So like you pick up the first value, you have both indices which are at 0. Then you advance the index on the x until the cumulative distribution does not surpass basically the sample in the y, right? And so, and then at this point you say, okay, I take this sample over here, which would be, let's say, x0. Then you consider the next sample, and you advance the cursor on the x until the value of the cumulative distribution is not above this number over here. And then once you do so, you observe that in advancing this value, you also took this value over here, because the next step of the y falls here. So you will pick up this value twice. This is more or less the mechanism. And it's basically summarized by this rather simple piece of program that I reported in the slides, and that you have available on the repository. Well, basically it does nothing else than what I was mentioning before. Assuming that it takes as input a set of weights, which is a vector of weights, which is can also be non-normalized. In this case, you just normalize it on the fly, and it takes as input an integer, which is the number of samples that we want to generate, right? Then you set to 0 all the samples, just to say that we pre-allocate our data structures. You compute the step. The step is this gap between the step is 1 over n, which is 1 divided by the number of samples. Then you draw the very first value, which is the famous y0. And then we start iterating. Remind that we do not need to expressively store the cumulative distribution. Given that we are going forward incrementally, we can estimate the cumulative as long as we move along the y-axis. So we have yy, which is the value of the uniform, basically the value of the cumulative distribution. We have cumulative, which is a accumulator that accounts for the cumulative distribution, and this is the index that is going to be sampled. At the beginning, when do you have to stop? You have to stop when basically you have finished the samples, when you arrived at the very end of your sample space with the second one. Like at the beginning, you start accounting for the cumulative distribution of the current index. The weight index is the first index. So now in cumulative, you have the value of the first element of the value of the probability of the first index. And then once you have the value of probability of this first index, then you have to look how many indices, how many of these dots over here, right, fall in the region, fall in the bar that you covered with the cumulative distribution. Okay? And then for each time you have that this index of probability of the sample is below the below the y, below the bar that you want to go on. But, well, basically you increment the index, you go on, and meanwhile you assign to the sample index, which is the place in the desired set of values, you assign to the sample index the index of the block that you're actually considering, and then you advance the cursor on the right. So now I read some questions. Sorry, if the sample is false, I keep talking the previous value. What do you mean, if the sample is false? That's latency. Okay, guys, let's do one thing. Given that there is a certain latency, I will answer the questions at the end of the lesson, when I will read all of them, because otherwise it's not efficient, this interaction with the chat. Meanwhile, if you, Tiziano, have time, you can answer to the guys. But anyway, I will answer to the question that the samples are not independent from each other. What do you mean that they are not independent from each other? We have a discrete distribution, right? Yes. Yes. Okay. Leonardo, if I have this, this distribution over here, right? And then I want to draw from this distribution of weights 2 million samples. Don't you think it might very well happen that I pick up a million times, so a gazillion of time this element over here? You might pick up the same sample multiple times because it's at random. But the important thing is that you pick up the very same sample multiple times with a probability proportional to the probability mass of that particular value of the input distribution. I hope I answered. So yes, you expect that samples will be repeated. Now, this is the mechanism. I invite you to run this uniform sample that I've given you in MATLAB, so in Octave, to try exactly. This happens because the distribution is discrete. And if the distribution is continuous, there will be no way. So you can't use this very same mechanism. You have to invert the y. Answering to Leonardo. Now, I invite you to run this piece of program. Well, you will have to next time, but I invite you to run this piece of program to get a feeling on how it works. Okay, because sometimes seeing it running and putting some print explains more than me talking for hours in 10 lines of code. Now, there is another, in the continuous case, no? In the continuous case, the situation becomes a little bit more complicated. Because sometimes we do not know the sampling distribution, so which means that we do not know P of x, or at least we do not know in closed form, or at least we are not able to calculate the cumulative density function. Okay? However, we know typically something about the distribution, which is we have a complicated program that might evaluate it pointwise. So imagine you have a function of 3000 lines that is P of x. So yes, you could calculate the value of one sample, P of x, but it takes you time. Okay? You definitely don't know it in closed form, because actually, like in a generic filter, let's say, or filtering process, well, the shape of the belief might be arbitrary. You have seen it in the discrete filtering case, where you might have multiple maxima or whatsoever. It's basically sometimes impossible to describe a probability density, but you might have an idea on how to evaluate it pointwise. Now, what happens if we would like to sample from this distribution, continuous or discrete? I recall we are able to evaluate pointwise the distribution P of x. Well, what we could do is to sample, to extend our mechanism and to attach to our samples that before were having all the same importance, all the same weight. We could extend the mechanism and represent, attached to each sample, a weight which is different potentially from every sample. With I denote a sample. Now, what happens if we have a distribution that we know, from where we can generate samples? Let's say we have a uniform distribution. There are pieces of program that, relying on the uniform distribution, provide you samples generated according to a Gaussian. So let's say, or some other distribution. Now, assuming that we have as input a known distribution pi of x, from which we can draw samples. and then we know enough of P of X so that we can stretch and fit and massage this pi distribution so that it basically is a little bit similar to P of X. Okay? We might, for instance, know that our P of X might take values or is bounded in a certain region of the state space, and in this case, as pi of X, we might select a uniform distribution that covers that area of the state space. Okay, just to give you an idea. Now, having said so, a way to draw a sample, a weighted sample from P consists in draw a sample from pi of X. So imagine you're generating the sample from the uniform distribution that covers all the area of P of X, all the area where we know P of X is active. Okay? You generate this sample, this value, this number, but then this number is drawn from a uniform, is not drawn from pi, a restricted uniform, but is not drawn from P, right? Then we use the weight to scale basically the value of the drawn sample. So this sample will have a likelihood, basically a weight, which is proportional to the value of P, the evaluation of P, which I can do. I cannot draw from P, but I can evaluate. Then this is a number of P divided by the value of pi in the same point. Okay? And this is called the importance weight. Now, it might happen, consider this example over here. I want to draw from this distribution. Let's just say that I don't know that it is a Gaussian. Then I might say, okay, instead of that, I could sample from a uniform distribution that covers enough the area where my P, which is the red one, is active. Well, I draw a generic set of uniform samples, okay, and I assign to each of them a value which is equal to the value of P in the sample divided by the value of the uniform in the sample. Okay? Of course, by doing this, if the two distributions are too different, right, it might happen that I have samples of neglectable value. For instance, this one over here is very little meaningful. Let's say that I was taking a uniform distribution which was going between minus 100 and 100. Basically, I had drawn weights that are, in the end, having a very low value. I had drawn samples that have a very low value. And in order to guarantee a proper coverage of the meaningful area of the distribution, then I might need to draw many samples, because a lot of them are wasted in areas where the weight is small. Okay? And then, if this is the case, I'm wasting a lot of computation, because presumably I will have to carry on samples whose weight was contribution basically to the generic representation of the density is negligible. Therefore, I could do a much better job, for instance, if I was restricting my sampling space to this area over here, as I've done, or, for instance, and even better, if I was sampling from a distribution which was basically as close as possible with the target one. Now, to the limit, imagine that we are able to sample from a distribution which is very close to P. What would happen then? It would happen that we draw samples more often, let's say in the middle, in the mean, and less often on the tails, right? According to what we want to have. But this is exactly what I want from the location of my samples. I want to have more when this distribution here is high. But then to each of these samples I will have to assign a weight, right, that is proportional to the ratio of the probability of the target distribution, of the value of the target distribution divided by the value of the proposal distribution in the point. Now, just to be evil, imagine that I sample from a distribution which is the union of two uniform distributions. So I have a uniform distribution up to here, and then here I have a uniform distribution with higher value, right? So like I have something like I go up, go to the left, go up, go to the right, so go up, go to the right, go up, go to the right, go down, right? So according to this shape, I will have substantially less samples here than here, because in this second part of the distribution, well, I have a higher value, so I'm drawing from that distribution. Accordingly, here I will draw less samples than here. But then, to account that in the right region I generated more samples, to the extent of approximating P of x, I will have to divide the samples generated on the right region by the value of the proposal on the right region, which is higher than the value of the proposal on the left region. So if in this part I have less samples, in this part I will have more samples, but they will have lower weight. And that's the principle, the mechanism behind a principle that is called importance sampling. So all I need to have is to have a proposal distribution. I need to have a distribution P of x that I can evaluate pointwise. I need to have a proposal distribution which is as close as possible to P of x, and then I can draw samples to from pi of x, which is my proposal, and then in order to simulate the fact that I was drawing from P of x, to each of these samples I attach a weight which is proportional to the ratio between the target and the proposal evaluated in the sample. Alessio, I quickly answer to you. No. Yeah, is equal to the first plus 1 over n. Exactly. But this is not the sample. This is the value of the target of the cumulative. We systematically sample the value of the cumulative. This was a parenthesis for Alessio. All right. Now, but there's one thing that we need to be guaranteed when we do the when we choose a proposal distribution for implementing this mechanism, and what we need to be guaranteed is that in every region where the target distribution is non-zero, I should have a chance of generating a sample, which basically can be boiled down to this condition over here. If P of x is greater than 0 in a certain region, then also pi of x should be greater than 0 in the same region, to denote that we need to be able to exhaustively cover P of x with infinitely many samples. If the target and the proposal distribution, the weight, are uniform, because basically all the information of the sample is in the sample position. Alright, now typically there is another mechanism that we need in order to proceed to the next part of the derivation, that is called resampling. It's very common that we want to turn a set of weighted samples, right? So samples that have this W, this weight, into a set that has no weights. To this extent, we need to, how to do that? Well, at first we need to, intuitively we have to repeat the samples that have a high weight and potentially suppress samples with low weight. But we cannot do this deterministically, because otherwise we lose randomness in the phenomena. So we could do it sampling the generating samples according to their weight. And this basically can be done by, let's say that W is a set of the weights of all the samples. So W with J is the weight of the jth samples. And we could generate indices. We could calculate the distribution of the indices, which is nothing else than the distribution of the weights. Then, trivially, we can generate an index from the index distribution, and this index will be generated with the probability which is proportional to its weight. Okay? And then, once we have this set of indices, well, for each of these indices, we pick up the sample that is corresponding to that index. So basically, the input will be a set of weighted samples, where xi is my sample and w with I is my weight. Then I could apply the function of uniform sampling that we have seen 2 slides ago or 3 slides ago to obtain a set of indices. And these indices are nothing else than the indices of the weights which are selected according to the value of the corresponding weight. So if I have a weight which is high likely, then it's very likely that the value I will appear here. And then, once I have this set of indices, I generate samples by selecting those samples that correspond to the indices I selected. Okay? So I have a set of weighted samples, I pick up the indices, I pick up the new samples with repetition from the previous set. Of course, I lose some diversity. I agree with you. I mean, there will be some sample which is repeated. Okay, there is some sample that is repeated. The next time I will inject noise, this sample will disappear. But it's just a way to turn a distribution which is having weights to a distribution that is not having weights. And basically this allows me to cancel, to delete, to focus my calculation with a set of samples which are concentrated in the area of my distribution where there is actually some probability mass, and I do not lose too much computation effort, which means samples, memory, in the tails of this distribution. Okay? Then I've told you resampling. I've told you the principle of uniform sampling, and now we come to the point that we can talk about probability distributions that are represented to particle densities. We can represent in general any distribution through a set of weighted samples. Imagine that this is a 2D distribution, 2D Gaussian. We could represent this 2D Gaussian either by its parameters, like mean and covariance matrix, or through a set of samples drawn from the Gaussian, and you can see here how they are placed. Likely I will have more samples at the center of the distribution, less samples on the tails of the distribution, but this is more or less what I expect. And like mathematically I could write this distribution of samples weighted as a set of as the sum of a set of Dirac delta function, each of them centered in the sample I, so the sample 1, sample 2, sample 3, and each of these Dirac is scaled by the weight of the sample. Okay? Now, of course, I lose the continuity in principle of my distribution, or at least in the representation, in this representation. Anyway, still the integral property holds, because if I want to know, for instance, how likely is it that my state falls in this region over here, all I have to do is basically count the weights, sum the weights of the samples that fall in this region over here. So I preserve somehow the integral property through this representation. So instead of having a finite number of parameters, I have still a finite number of parameters, because I'm talking, I'm still on a computer, but I have a very large number of parameters. And with these parameters I could represent arbitrary densities. Also, if I have a distribution which has 2 maxima, well, I could represent it by putting a bunch of samples here and a bunch of samples here. Okay, now, that's why the particles are cool. They can represent arbitrary distribution. They are easy to visualize because you just draw a set of dots. And the more dots in a certain region of the state space, the more likely it is that this density falls in that region. They are easy to manipulate because, for instance, if I want to project a set of samples to a function, I could just take each of these samples and throw it into the function. I get a new sample, and that's gonna be the sample of the p of y, basically, where y is equal to f of x. And they are good for small state spaces. Remember, if the state space is low dimensional, it's fine. Now, as always, we have defined here how to represent my distribution. With the Gaussian, we have the set of parameters, or the unscented. Now, we will have to say how to carry on operations on this density. Okay. Now let's proceed. Sorry, 1 second. The first action is how to transform samples, right? So that we have already seen it with the unscented transform, and it's no different in the case of the set of samples. If I have a probability distribution P of xa that I represent as a set of weighted samples, W with I and Diracs, well, and I have a function xb which is equal to f of xa, I could obtain the sampled density of xb, which is a random variable distributed as xa, p of xb, just by taking each of these samples and applying for each of these samples the function f. And this will project me this input space in this output space. And what do I do with the weight? Well, with the weight I do nothing else than than preserving the weight that I had before. Okay? And this is nothing spectacular. And I write it this way. So I have p of xb, which is equal to a set of delta function centered in f of xa with I. This I denotes the number of samples. I think you're not surprised by that. And this is for the transformation. Then for completeness, I also talk about marginalization. Well, marginalization is kind of straightforward. We always know that marginalization consists in suppressing basically some coordinate of my density function. And how do I marginalize? Well, straightforwardly, assuming that I want to marginalize over this is xa and this is xb. If I want to marginalize out xb, I just delete the distribution, delete from each particle the components or the coordinates that correspond to the variables I want to marginalize out. And I think this is straightforward, and it's equivalent more or less to what we were doing with the unscented transform that we have seen last time. And then we go on, the chain rule. How do I implement the chain rule? Well, once again, the chain rule requires the ingredients. We have an input distribution, which we call P of xa, which is consisting of a set of samples, no? Dirac centered, which is a set of Dirac delta function, weighted Dirac delta function, centered into the values of the samples in my distribution. I have a conditional distribution P of xb given at xa, assuming that I'm able to generate a sample from this conditional distribution. Assuming that I am able to generate a sample from this conditional distribution, well, straightforwardly, I could generate a sampled density of the joint distribution just by picking up a sample, applying to this sample, using this sample over here to generate a new sample of xb because xa is known, right? So I generate a sample on the conditioned distribution because I said that I'm able to generate samples from here. This is a constant. And this basically gives me the other part of my joint distribution, which is this part of the vector that I put in the new as center of the new delta, which will now be living in a state in a space having a higher dimension, having dimension of xa and xb plus dimension of xa plus dimension of xb. And I think this is obvious. Okay. Now, this all was straightforward. I will answer to all the questions that Tiziano didn't respond to at the end of the pack of slides. Otherwise, the explanation gets broken like into too many little parts. Then there is the last action that we need to implement on this distribution, which is conditioning, right? Conditioning, we all know what it means, assuming that we have a sample distribution in this form, which is a joint distribution. Here you see the contribution of xa and the contribution of xb that we could visualize as this set of weighted samples over here, and then we have a certain value xb that would slice our space, and then we say, okay, now I want to have the conditional density of p of xa given xb, which is the value I know. Well, this can't be done because with the samples it's tough. You might try to do some black magic to interpolate things, to go through the continuous, but it's not easy, let's say this way, and then you might do worst. So forget about doing conditioning if you have a distribution represent in an easy way. If you have a joint distribution represented in this way, as a set of samples, and then what do we do? We need conditioning for implementing our filter. So, well, we could just, as the good old engineers do, we relax the problem. And we say, okay, you know, man, I have a sample distribution, but I have a sample distribution which is not fully sampled. It's a mixture of a sampled distribution and a closed form, a conditional, let's say, distribution. So imagine I have a two-dimensional distribution, right, where one element, xa, is sampled. Okay, so in this case, let's say I have 1, 2, 3, 4, 5, 5 samples. Okay, so I will have 5 samples in total for this distribution. But while one set of coordinates of this sample, of this element, is a sample, the remaining part, the remaining coordinates of this sample over here, so the coordinates that span over xb, are described by a formula which is a closed form distribution, which is p of xb given xa. Xa, which xa? Well, given the xa which is attached to the sample. So I could visualize this as having a sample in this space, and then having along this axis a density of the possible values of xb given xa. Observe that this Dirac lives in the sampled space, and this xb gives in the orthogonal space, so lives in the other set of coordinates of the sample. So I do not really have a joint distribution represented by a set of samples. I have a joint distribution which is represented as a mixture between a sample to which I attach a conditional distribution over the conditioned variable. Okay? Now, if I have a distribution in this way and I apply conditioning on the variable xb, well then slicing it might have a reason, because slicing it might end up in this. I could evaluate this value for this xb, which is attached to this sample here, xa, and I could evaluate this value for this xb, which is attached to this sample over here, while it will have 0 elements. So intuitively, if I condition on this value, on this particular bar over here, I will have that after the conditioning, this sample over here will have a decent value. This sample over here that corresponds to this conditional will have a decent value, while these other samples here are likely to have very small values, just intuitively. Okay? Now, to come back to some derivation, here it's how to do it. So my input is this joint distribution, which is expressed as a part, which is a sampled part, and as a continuous part attached to the sample. Okay? This continuous part, of course, is controlled by XA, by the sample itself. So this and these are the same. Now, in order to calculate P of XA given XB, what you all would do is to divide this distribution by the known value of XB and evaluate this P of XA and XB by blocking the value of XB, which is the conditioning value, right? So, straightforwardly, this can be done just by applying the rules of probability that we all know. What is P of XB? Well, this is nothing else than the integral over all possible values of XA of P of XA and XB. Marginalization. That's what we have on the bottom. This is just the application of conditioning according to the probability rules. This is where we start from. I assume that none of you is surprised, is impressed by this formula over here that stems directly from the definition of probability. All right, then if I take this and I plug in the definition of P of XA and XB specialized to our I need to drink to this particular shape of a distribution, well, I end up, query replace, I end up to the second floor of this machinery, right? Where here I have the integral of the very same thing integrated over dx. Now, for a moment, let's focus on the denominator of this equation over here. Now, let's look what we have here. This is a Dirac delta function. I have an integral of a summation, and inside the summation I have the Dirac, right? But the Dirac is active only over XA, right? Now, it turns out that you could easily flip the summation and the integral, because this XA with I, given that I have a Dirac, will just like be active in one point. So I could pull out this P of XB and XA from the summation, okay? Together with the from the integral, together with the summation. And then what stays inside is nothing else than the Dirac delta function integrated over XA, integrated over XA. And by doing so, basically you all know that this element here is equal to 1. So what remains on the bottom floor is the sum over I of the weights of the conditional distribute of the sum of the weights of the original weights multiplied by the conditional distribution of the sample evaluated in the conditioning variable. So this element over here stems basically from the manipulation that we have done on the denominator, because this part here gets cancelled. So what remains to evaluate is the upper floor. and for simplicity I just report it here. So just the normalizer is out of our universe, but we always know that the normalizer typically doesn't even need to be computed. Okay? Now, what do we do with this density over here? Well, this density over here is just the response to our query. I remind you that we do know the value of xb. And since we know the value of xb, this p of xb given xa is nothing else than a number. Therefore, our sampled distribution will be obtained by the original distribution just by evaluating the, considering that the normalizer is just a constant for us that we can call it n, we could just like boil down the entire evaluation of a conditional to take this special joint distribution, and for each input weight we multiply the weight of a sample by the likelihood of the measurement of p of xb given that particular sample. If we are able to evaluate this number, this entire quantity over here becomes our new weight after conditioning. This eta here takes the function of a normalizer, and as all normalizer, given that we have a sampled distribution, we will this will result in scaling the weights basically so that they sum up to 1. Okay? And then, well, and then I have implemented conditioning. So, boiling it down to implement conditioning, I do not move the samples. The samples stay where they are, but what I do is that I multiply the weight for each sample by the value of the conditional distribution of the measurement given that sample. And this basically mimics what I was mentioning before. If I condition on this special joint distribution on this value, well, this sample over here will receive a weight which is proportional to the weight he had before, and multiplied by the value of the conditional distribution evaluated in the specific conditioning value xp. And this will either increase or decrease. Well, normally it will always decrease, but then there is the normalization action that lifts everything up. Okay? Now, this is said, done. Now we have everything, right? Don't we? We have all the ingredients to implement or to derive this new family of filters, which are the particle filters. Okay? And then we start. Here it is. We start with the thing which is a dynamic system. You are shocked, I know, that this is the usual dynamic system to which we have this, let's say, additive noise, just because I don't know. Well, I have my funky additive noise, I have my observation model that shoots out observation, and I have my transition function xt minus 1. I mean, this could be also replaced by the transition model p of xt minus 1 given p of xt given xt minus 1 and ut minus 1. But yeah, it's the usual model that we have. We assume to know the transition function. We assume to know the noise distribution. And we have our belief represented as a set of Weigett samples. Okay? Now, and another thing that we need to have is to have a machinery that can evaluate pointwise the observation model. So, if I give you this number and this number, you need to have a routine that gives me the value of p of zt given xt. I do not need to know it in closed form. I just need to have a piece of program that if I give you a value of z and a value of x, returns me the number that corresponds to this this function evaluated in the point. Okay. This is the setting, and now let's look what we can do. The prediction, right? We start, the prediction is the step where we incorporate the control. Now, our ingredient is p of xt minus 1 given xt minus 1, which is our belief at the previous step, which is represented as a set of weighted sample centered where they should be. We have a machinery, we have a noise distribution. Let's assume that we have a noise distribution, all right? Like we have a machinery that is able to generate samples from the control noise. Okay? Well, if we assume that the noise is Gaussian, we could have a machine that generates Gaussian noise, and then we are able to generate a realization, to generate samples of this noise distributed according to the parameters of NU. Or can be anything, but at least I should be able to generate samples from the noise. Now, in order to predict the next step distribution, the most straightforward thing is to basically take for each sample of my target distribution, I take a sample of the noise. How many samples of the noise? Well, for each sample of the input distribution, I generate a sample of noise. This is equivalent to generate a joint distribution. And then I attach this noise to the control, and with these values, the values of the sample and the individual values of the noise attached to the sample, I perform the prediction. Okay? So I evaluate the function. Note that the values of this is a value of a Dirac, right? This is a number, a very specific number, which represents the center of the Dirac at my next state distribution. So I transform each sample with its noise through f, and this will move me to the next point in the state space. That's it. I don't need to do anything else. Given that I know how to sample from NU, I do not have to change the weights. Everything stays as it is. So I can easily say that my next distribution of samples, so the generic sample xt given t minus 1, will be equal to the evaluation of the function done on the original sample and on the individual noise element instance of noise drawn from the noise distribution NU. And the weight, well, the weight, as you might expect stays the same. So, for doing the prediction, we do nothing else than using the transfer to function. And also would be the chain rule, because we expand the sample by attaching this independent instance of NU, and then we project everything through F. This is the predict. And what about the update? Well, for the update, it's quite easy, because what we do, what we need to have for the update, I remind you that was part of the specification of this instance of filter to possess this distribution over here, this piece of program over here, p of zt given xt with I. Okay? So, if this is our set of states, no? Our states, I could, so our hypothesis on the predicted state, which is still represented by a sampled distribution, I could straightforwardly generate the joint distribution just by attaching to each of these samples the conditional distribution of the measurement given the value of the sample to which I attach it. In this way, realizing that mechanism of a sample and the conditional distribution. Okay? It's a form of chain rule. Actually, it is the chain rule, because you have to consider that the sample concerning a Dirac, a sample is unique, right? So it's just one value. And so this probability density here is perfectly legit. It's not that I have to do any blurring or anything. This is known, and so this is blocked. This is nothing else than a distribution over Z. That changes, of course, like for each sample. But part of my ingredients required, basically, there's no way that I have to store this object, right? Part of the specification required just to be able to evaluate this number over here. Because if you recall conditioning, in order to incorporate a measurement, all I have to do is to take each weight of a sample and multiply each weight of a sample and multiply it by the evaluation of the transition model at the conditioning measurement given the sample that I'm going to evaluate. And this will basically lift up samples, which are called particles now, that have a high value, and lift up means assign a big weight, and assign a small weight to particles that have a low value. And what happens with conditioning to the samples? Well, nothing happens. The samples stay where they are. Only the weights change. And then what could happen with this mechanism? Well, what could happen is that you basically inject diversity in the samples. So when is the situation where you inject diversity, which means you perform some random operation? You do it only in the predict, because that's only in the predict that you sample noise. And this noise here will be different for every sample. So, well, by doing this mechanism over and over, without any further routine, what you will have is that the samples only move according to the prediction model. And given that the transition model, and given that the transition model typically injects noise, what you might expect is that your distribution of samples gets spreader and spreader over time, right? It opens up immensely, if it's not already open. And only the weights will change. They will change according to the update done by multiplying each original weight with the likelihood. But as a consequence of this, we will have that some weights will have a very, very small value, and some other weights will have a huge value compared to the others, right? And then we are with a computer and we want to be fast. So, well, it's quite impractical to carry on a huge number of samples if only a subset of them is meaningful to me. So it makes completely sense to resample or to kill the particles that have low weights. And how do we do this? With the resampling mechanism that we have seen a couple of slides ago. In this way, basically, the samples having a high weight will be repeated. The samples having low weight will be suppressed. And at the next update, each of the samples, even if I have repeated many times one single sample, at the next update, this sample will diversify, because to each instance of to each of the samples which are originally in the same position, I inject a control affected by a different sample of noise. So they will diverge in the subsequent round. And well, that's more or less the wrap-up of a particle filter. It's not the most complicated algorithm in the world. To do the predict, well, I start from a set of samples. For each of these samples, I draw an element, a sample from the noise distribution, and I alter the position of the sample by applying the transition model, the transition function. And that's it. To do the update, I basically only change the weights of the sample by multiplying the original weight with the evaluation of the observation model in the sample itself, and I leave the sample where it is. And then, mandatorily, I have to resample these new samples to make a generation of samples that have uniform weights Otherwise, I will over time I will lose computation. I will lose resources uselessly. And then that concludes the lesson. Now I'm up for the questions. Tiziano, did you answer to everyone, or guys? You can if there are still questions that have not been answered, please write them down. Alessio, okay. I'm staying tuned to see if there are additional questions. Alessio, did I answer you? Or did you find the explanation to your question? Do you still have it or not? No? Yes? Maybe? Brr. Okay, I think you can ask me questions in the mid session then, and I would now leave the... Leonardo, depending on the problem, in general, having a good distribution is of fundamental importance. Leonardo asks, how important is to take a good distribution? I would say quite important, especially when the state space is high, but for small state spaces you can do basically what you want. Uniform is really a butcher thing, but if you have seen in this example or in this dissertation, we didn't really sample from the uniform. We were sampling from the noise, right? And the noise typically we know, or we can model. Then I would stop here, and I will leave you to Tiziano for the explanation on UKF. We could do it straight away. So ciao ciao, and Tiziano goes on the stage.
Okay, everyone is here already. Can you hear me, guys? Sa. Okay, still I have a bit of delay. Okay, thank you, Emanuele. I think that most of you are already here because we attached almost to the previous link, I guess. I see the chat. So, okay, I will start right away because we have just half an hour. So let's try to be fast. So today we are going to see the application of localization using the unscented Kalman filter, right? So we will basically take the same scenario as the AKF localization. So we have the classical Orazio robot, so a differential drive. We are perceiving 2D points, and in this context, we have the data association, which is known. Actually, to extend this exercise to unknown data association will be enough to copy and paste the exact same function that we see the last time, I guess, and bring it here. Of course, in this case, you will have a localization code with unknown data association, which is sort of a mixture of the previous exercises. So that is what I've just said. So the map is known. Our sensor can perceive 2D landmarks, and the robot is controlled as usual with V and omega. Now, how we change approaching the problem? We still have to define the state space, the measurement function, the control, the measurement space, the control space, transition function, and observation function, but in this case we just don't need Jacobians because we will use the property of the sigma points representation of the Gaussian to perform both the prediction step and the correction step, right? So to all this part I will go really quickly. As always, we have the map represented as 2D landmarks. This is our domains, so the 2D pose is an SE2 object we represented with a 3D vector. Then 2D controls and 2D observations in this case, because we observe the full point, so we don't have bearing observations or a monodimensional observation, whatever it is. So same transition function actually, so Euler integration of the unicycle model, and same measurement function. In this case we are working on localization, so it means that we know the position of this thing. That's the main difference with SLAM, and in that context we were estimating also this guy together with this other guy. In this case the map is known, so basically this value is constant, right? So as always, control noise, we take the same exact control noise model as the last time, so a squared term in the velocity plus a constant term. Measurement noise as always. So until now actually nothing changed between the EKF and the UKF, meaning that basically all this part is problem related in the sense that it depends on how you model your problem. These things will always be there. Then depending on the filter that you apply, so it might be an AKF, an UKF, or in the next lecture we will see even the particle filter that the professor just explained. This change some blocks inside the algorithm, but all this part that I just speak about, state, controls, measurement, functions, blah blah, this is all problem related. So it's not related to the algorithm, it's related to the problem, okay? So UKF wrap up. Now we will go in the detail on each single step, so to see how we can translate those formulas inside the actual code. So here we have the Gaussian, which is we represented here as a joint distribution between the state and the controls, right? So we have the two means and the covariant matrices. Then we perform the Hansen-Ten transform, so we get a sigma points representation of these two guys, so both the state and the controls. We take these sigma points, we pass it through our transition function, which is non-linear, but for the fact that in this case the Gaussian is represented by points, we can basically apply this function to each sigma points to get another set of sigma points as output. Now, of course, those sigma points contains also the controls, these guys that represents just the state Gaussian, let's say, the state distribution, okay? So once we have done that, we can compute our predicted observation using the observation function directly, so same process as before. Even if it's non-linear, thanks to the representation of sigma points, we can apply it to the Gaussian. And then computing these quantities using the reconstruction formulas from the Hansen-Ten transform. So we will compute the cross-correlation term between the state and the measurement, the covariance of the measurement, and the mean of the predicted observation, let's say. This is, of course, the covariance of the predicted observation. Now, we cannot condition sigma points because it's represented point-wise, so we have to come back to the classical representation of a Gaussian, so mean and covariance, and then apply the Kalman correction expressed by those formulas. Okay? So let's divide all of this in different steps. Of course, the core of the algorithm is the computation of the sigma points, for which you have the formulas. We have a couple of hyperparameters, 3 hyperparameters actually, which are the magic numbers lambda, alpha, and beta. The professor gives to you some standard value that actually works most of the time, let's say. It has some theoretical background for this choice, but you can just use it, and if you are interested in other values, you can just read the original paper that the professor leaves on the slides. So once we define these values, how we compute sigma points? We define the parameter lambda using alpha square times the dimension of our problem, so the dimension of our Gaussian. Compute the Cholesky decomposition of the covariance. A, in this case, is actually the sigma, so the covariance of the Gaussian. Compute the Cholesky decomposition, so that's how we compute the sigma points, so the actual point, and this is how we compute the weights that are associated to each sigma points. We have one weights for the mean, and then we have weights that are used for the reconstruction of the covariance. Okay, so this is how you go from standard representation to sigma points, and here is the code. So how you have to translate them, I reported here, so it's easier just after the theoretical part. So given a mean and a covariance matrix, you have to return the set of sigma points, the weights for the mean, and the weights for the covariance. So far, so good. So now we know that if I have a covariance, a Gaussian of dimension n, I will have 2n plus 1 sigma points. Okay, so I actually have more parameters than the classical representation, but at the same time, I gain the capability of transferring this Gaussian through nonlinear functions. Okay, so setting the parameters, here I will initialize the variables, and here you have just to apply the formulas. These are for the 0 elements. Of course, underneath you find also other pieces that have to be filled to compute all the other sigma points and all the other weights, which is really straightforward. Okay, they are. Okay, so here we compute the Cholesky decomposition, and here you have to apply the formulas for the value of the sigma points, while for the weights of the mean and the covariance, everything is really straightforward. Okay, so now the reconstruction, so coming back from sigma points representation to mean covariance. Okay, so the canonical form. So the computation is really easy. Basically, the mean is a weighted sum of the sigma points. You can interpret it like that. And here, after you have the mean, you are basically computing a weighted covariance matrix, weighted by this guy, using the classical formula that you will use if the sigma points were just data points, right? If I have a set of data points and I want to know the covariance, the mean and the covariance, I will follow exactly these formulas, eliminating the weights. So the weights actually tells me each of these points how much probability mass it brings with it, in a way. Okay. So, and for the reconstruction is exactly the same thing. We have this really compact function that, given the sigma points, the weights from the mean, the weights from the covariance, perform the computation. So a weighted sum, basically. Now, how you have to debug this thing? That's of course really intuitive. You just take a Gaussian, whatever it is, you can generate it at random manually. Then you compute the sigma points and you come back. If you obtain exactly the same distribution, it means that the two functions are the same, or you compute two systematic errors which correct each other, which can always be. But in 99% of the cases, it means that the function actually works. Now let's go inside the filter. So we see the two transformations. So from, let's say, mu sigma representation to sigma points. Now let's go to the prediction step of the filter. So as I said before, what we have to do, constructing this distribution. So we have our mean and our covariance, apply the function that we just see, so computing the sigma points. To each of these sigma points actually represent both a state and a control. So you can imagine in the case of a unicycle, it will be a single sigma points will represent x, y, theta, ux, u theta, right? So I take this sample and then I apply the formula for the transition. So I will take the first three entries, that's my state, and then I will apply the controls following the Euler integration of the unicycle. This will move the first three entries, so the robot state, by something. This something, like the output of this function, will be a sigma point in 3D, because it will be x, y, theta, that represent the robot location. So really easy. And I have 2n plus 1 of them, so if in this case, the dimension of my Gaussian is 3 plus 2, so it's 5, so I will have actually 11 sigma points, right? So then I have this set of guys, and these are the formulas that we see before, right? So far so good, okay? Of course, here we change the position of the sigma points, the weights doesn't change. In a way that's really similar to what you see just about 15 minutes ago with the professor speaking about the particle filter. So the application of this function just moves the sigma points. It doesn't change the probability mass that these sigma points carry with them, okay? So that's our fantastic code. So as always, we take mu sigma and the transition. We extract the velocity, computing the noise model for the controls. So that's our covariance, right? And then here I initialize stuff. This is the sigma xu, so the joint distribution state controls. I will put the corresponding covariances in it. Then I compute the mean of the same distribution. So mu, control on the translation, control on the rotation. I will pass this distribution to this amazing function, which gives me those quantities that we just discussed. And that is basically, for each sigma point, I will extract the state, I will extract the controls, and I will apply the motion model. And this will constitute the sigma points in output. Of course, the weights will stay the same. So exactly the same that we compute in this step. Okay? The code is clear, guys, until now? Everything clear, or you have questions? If I'm going too fast, just tell me. Let's see. Okay. I assume yes. Okay. So now the correction step. So the update. So the first half of the update is just to take the sigma points that we have just computed after our prediction step, pass it through the observation function to get sigma points over the measurement space, right? So in the case of this specific filter, in input we will have sigma points of dimension 3. Yeah, of course, I totally understand. So the sigma points are 3D. My observation is 2D, so the dimension of the sigma points, of course, will be 2 times number of sigma points, right? Exactly the same. So we have 5 at the beginning, we transform it in 11 sigma points, we apply the function, this stays 11 sigma points of dimension 3, and those will be 11 sigma points of dimension 2, right? So the number of sigma points, of course, doesn't change if I apply a nonlinear function, right? So then I have to compute the quantity that I need for the actual Kalman correction, let's say, okay? To compute the Kalman gain and all the cool stuff that we see until now. So you have those guys, compute a weighted average to get the mean of my predicted observation, right? Then I have to compute also these terms, which will be useful during the second part of the update. That's the cross correlation term. So if I take the formula of the covariance reconstruction, in this case, of course, I have to consider in one side sigma points and the mean of the sigma points for the state. So this guy, not the output of the function, this guy. And on the other side, the sigma points for the measurement and the corresponding mean. That's why I computed here. So actually I have to reconstruct the mean of the state, reconstruct the mean of the predicted observation, right? Once I have those two quantities and I already have the weights, right? Because this weights doesn't change when I pass it to this function, I can compute this sigma xz in closed form. So the computation that is required for the first half are these two weighted sum, okay? And actually, if you notice, these two weights are actually the same, right? Because when I take those guys and pass it through this, weights doesn't change, okay? Right, now we do that So we have all the pieces that we need to compute the amazing joint distribution. So I see a message. I was going to read it immediately. So we have those pieces. So at first we have to compute the joint distribution of the state and the measurement. Notice here I don't put the comma, and I mean a cross correlation term, right? Here I put a comma, and I mean the joint distribution. So pay attention to the difference, right? So I have all the quantities that I need. I already have reconstructed these two guys. So I just put it together to get the mean of the joint distribution, right? And then I have the corresponding covariance. So this guy, I can reconstruct it really easily because I have this and I have the sigma points over the state because that's the output of my prediction step. So I can compute the sigma x easily. I compute this guy, and this guy is just the transpose of it, right? Because the covariance matrix by definition is symmetric. Okay. So what is this guy? This guy is actually the sigma z that we use also in AKF, which was constituted by the constant term on the diagonal. So is the uncertainty introduced by the correct measurement. Okay. So we know that the measurement is distributed like a Gaussian. That one is coming from our sensor. So, and this represents exactly that. So I take the one of the predicted, let's say, and I sum it with whatever noise affects my sensor. Okay? So once I've done that, I have the complete joint distribution and I'm happy with it. So, how is implemented? I will not read code for you, but you can just notice here that we leave the ID of the measurement known, meaning that you know the data association. So you take the sigma points, pass it through the measurement function to get the prediction. You repeat this process, of course, for all the sigma points. So once you have this guy, you can insert it in the sigma points for the measurement, right? And you continue like that for all the state space sigma points, getting, as I said before, 11 sigma points for the observation. So second part of the update, you just reconstruct mean and covariance that we just see. So the covariance sigma z, the covariance of the state, because we already know that we need that, and the sigma noise, which as always is that constant part that I was just speaking about. Then we take the sigma xz and we just fill it up stuff. This thing, this loop is actually this computation over here. Right? So I need, let's say, a delta x, meaning the value of the sigma points minus the mean, and the same for the z. So the value of the sigma points over the measurement minus the corresponding mean, and here I apply the reconstruction formula, okay, to get the cross correlation between state and measurement. Okay, that's right. Then the second part of the update is super easy. Actually, of course, I don't have to compose the joint distribution. I will just take the pieces that I need to perform conditioning. I cannot perform conditioning in the sigma points space, let's call it, because I cannot slice individual points. So what I will do actually is that I perform the observation step to get sigma points over the measurement, and then I will immediately reconstruct the pieces of the distribution that I need. All of these, as we see before, are pieces of the joint distribution. So I will compute them individually without assembling the whole thing and just apply the Kalman correction, right? And you can recognize that this piece over here is actually a Kalman gain, okay? It's exactly the same formula. Here we put it explicitly, but you can check that it's exactly the same as we see in the AKF. So programmatically speaking, you compute the K, so once you have the pieces, and then you have just to compute the innovation, apply the correction to the mean of your distribution, and apply the correction to the covariance. Once you have done that, that's fine. So you have your new distribution, and then the process starts again. So combine it with the controls, compute the sigma points, prediction, correction, over and over and over again. What's the advantage in this case? as you see, we don't linearize our system. So you can see sigma points as a sort of second order approximation of a Gaussian. So when we compute the sigma points and pass it through a nonlinear function, we are performing a second order approximation of the output Gaussian. So it's far more accurate than just performing first order propagation, so computing Jacobians. But of course, if I take a Gaussian and pass it through a nonlinear function, the output is non-Gaussian in general. So that's always just an approximation. Okay. So now the hands-on, we have just 5 minutes actually. So I will ask Giorgio if he thinks that because the code is already here, like I already explained it. So maybe the guys can try to do it in the weekend, and I can start from this one next Tuesday. But the boss says, I evoke you, boss. The final result? Ah, yeah, sure. Why not? I have to find it out, actually. Okay, that's nice. Reaching, so let's go directly here. Source. Okay. Yeah, I was having delay. Okay. Now I start from a random location that of course broke it immediately. Let's see. Yeah, okay, better. Okay, so that's the final result. Of course, you don't see the exact covariance because we don't plot it. Most of the steps are carried on in the sigma points formulation, but you see that after a small transient at the beginning when it was delocalized, after integrating multiple measurements, you finally get to the current location, let's say. Of course, in the program, as in the other cases, sometimes you just run it. It's starting from a random location. Sometimes following the transition, it can be outside of the map, and of course you cannot recover from that, so you have to start it again. That's what happened. You see that in most of the pieces, your covariance is so small that you cannot see it, as in previous cases, but you observe also that when he was following this curve, for a moment, let's say the covariance was like visible, and that is due to the fact that even if you can fully observe a landmark, that was probably not enough, given the noise on the controls, to estimate as accurate as before the robot location. Okay, so I think that is it. So you have to basically write down the two transformations and then fill just the formulas that you find on the same slide of the exercise this time. So I will stop it here. Also the program decided to stop. So I would say, guys, that is it. If while you are doing that by yourself you have any question, any difficulty, of course you can always contact me or Giorgio, and maybe if I receive enough questions, let's say, maybe we can take it together. We can try to do it together in the next lecture if there are lots of doubts. There are any questions? Giorgio is proposing to add it as an exercise. Actually, guys, if I have to be honest, in fact, you can use the same code, and by adding the pieces that we shown you for the EKF, you can basically reach the same result. Like you start from the localization. If you insert the module to compute the data association, you can do a sort of realistic localization problem. Then by adding a piece that extends the state, actually the same piece that we see before, by including the landmarks, then you will have, let's say, a complete SLAM system, even if of course it's simulated, that uses UKF, and you can also realize how much memory in general the UKF consumes with respect to the EKF when you have a large state space. Even another cool exercise, if you want to just practice something, it will be to take the UKF localization code and try to use the bearing observations and see what happens and see maybe if it performs better or not with respect to the EKF. Okay, that will be also interesting. So basically, you can play around with this code however you want. UKF Slam is a really good exercise because it allows you to revise everything that we see until now. So the data association and blah 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 blah. Okay. So we arrive precisely at 4. If there are no questions, or if Giorgio want to say something, I will close the live. Okay. So we'll wait 1 minute and then close it eventually. There always a delay like incredible. Yeah, definitely. Yeah, sounds nice. So guys, have a nice remaining of the day, let's say, and see you next time. Bye.